Hi, my name is McGrath Gomez, and this is the Extra Credit Project, aka Project number 10 for Professor Bautista, Calculus 1. My student ID is 1252320. So in this project, we're going to examine what is the volume of a solid in revolution. So to kind of give you a hint, it's basically just going to be spinning around an axis. So if you take a two-dimensional solid, spin on it. So if you spin it on an axis, either the y-axis or the x-axis, just as we find the area underneath the beneath the curve or underneath the curve using small cutouts or small rectangles. So if you can kind of picture when we did definite integrals, we kind of did an area, and where it's highlighted by the pink is basically we found that area of that using small indefinite rectangles. So I'll put this in blue. So this is basically how we found the area, right? To take an infinite amount of small rectangles all throughout the graphs from intervals A to B. So we're going to do the same thing, except this time we're going to be spinning it around an axis, either through the x-axis or even through the y-axis. Just as we find the area beneath the curve using small cutouts or rectangles, we will also do the same by chunking discs or washer sections in a solid in revolution. So just picture a solid that's spinning. If we take the definite integral, we spin it around, it becomes kind of like a vase-like thing, and we're basically just going to try to find the area that it occupies, as you can kind of see over here. But instead of just doing one side, we're going to do both sides, right? So this is what we're going to be doing. This is kind of like an advanced application of integrals. So if you picture your integral and you spin it around, that's basically what we're going to be doing. The reason why it's called a disk and a washer method, to kind of separate, is when the axis of revolution is perpendicular to the integration variable. So basically the y-axis, right? So whenever you're doing this, you're revolving around the x-axis with respect to the x, or you're revolving around the y-axis with the respect to the y-axis. So if it's flush against the x-axis, there is no gaps. As we can kind of see over here, there is no gaps, right? So we're going to be using something called a disk, because there are no gaps. They're just discs of the actual chunk that we're going to be taking. Because if you spin a flat surface around, what do you get? You get a disk. So we're going to use this formula for x-axis, which is going to be v is equal to the integral symbol from a will be our lower limit, b will be our upper limit, pi times f of x squared dx. For the y-axis, we kind of do the same thing. All we really do change is instead of the f of x is going to be like f of y or g of y squared. And then instead of d of x, it's going to be dy. And where x is equal to g of y. Now, the washer method, if you remember correctly, right, the washers have a hole in them. You can kind of think of them as like a donut. So when there's a gap between the region and the axis of revolution, and you still form a disk with a hole in the middle, that's what you get, a washer. So basically, it's just a disk with a hole in the middle. Because sometimes you might have gaps like this or this. And if you spin it around, what do you get? You get a little washer. So for that, it's kind of a very, very similar formula. For x-axis, it's going to be v is equal to a lower limit to b upper limit. The integral symbol, of course. If you're not sure, this is the integral symbol. This is called the integrand. Pi times r of x squared minus r of x squared 2, but I put it in lowercase just to kind of differentiate. This is the bigger size, and this is the smaller area, dx, where r is outer and the lowercase r of x is the inner. You can And for reference, I use the bigger and the smaller. That helps me understand that this is the bigger part of the circle versus the smaller part of the circle, which I just put as lowercase. If it helps, you can always put different variables. You don't have to use R and R uppercase and R lowercase. You can always use like F of G or A of B or X and Y, or even just about anything. For the y-axis, it's just about the same. So it's going to be v is equal to lower limit c, upper limit d, because I'm writing these variables, pi, and pi times r of y squared minus lowercase r of y squared dy. So if you notice, where in the y-axis it's going to be r of y, and even in the inner part it's going to be r of y. So the only thing that really changes is the r of y. So Professor Dave kind of explains this in a little bit. So if you take the cross section of a circle, so if you remember how we find the area of a circle, right? What's the most important thing to do for an area of a circle? You need to find the radius. So your radius is basically your y, your y value. If you take a cross section of it, so if you chunk it, in green I have the disk, so that's kind of like where you have the disk. And to find the area of that, it's just going to be pi r squared. If you remember correctly from trig or geometry sometimes, and then from that we are going to transform it into a is equal to pi y squared. And instead of y squared, what we're going to do is x squared plus y squared is equal to r squared, right? And then we're going to make y squared equal to r squared minus x squared. And then we're just going to enter it back into our original equation of, instead of y squared, we're just going to insert this function. So another name for this is going to be composite function, because we're going to be inserting this. It's going to be pi times something. Just like it shows pi times y squared, we're also going to be finding y squared, and then we're just going to be plugging this in. So that's for a two-dimensional shape. What if we want to do three-dimensional, right? So what if we do a three-dimensional shape? So if you can kind of picture a sphere, because a sphere is the three-dimensional version of a circle. The equation for it, it's going to be pi to negative r to positive r times r squared minus x squared dx. And because it's you're doing basically just one half, right? So you're doing this right here and then this right here. Because there's two hemispheres, there's two halves of that sphere, you're going to double it. And you are going to essentially get, and this is how you're going to derive the formula, 2 pi, integral symbol, 0 to 2, r squared minus x squared dx. Once you integrate and you find the antiderivative, you're going to get 2 pi times r squared x minus x cubed over x3 r upper limit and 0 lower limit. And if you evaluate for x further, what you're going to get is the volume of a sphere is equal to about 4 over 3 pi r cubed. So if you don't remember the antiderivative rule, it's basically the chain rule just in reverse, right? So if you don't remember this, we are going to write it in purple, just to kind of reiterate. So basically, you don't know how to find the antiderivative. It's basically the integral symbol, x to raised to the n power dx. That's what you get, right? Like these are kind of like the equations you get. Let's write this a little bit neater. And once you find the antiderivative of this, there is a rule, right? So it's going to be x to the n plus 1 over n plus 1 plus c. So if we follow this same formula and insert this over here, that's where we get the volume of a sphere. So you can kind of think of this as like the anti version of like a derivative, right? So that's why they call it an antiderivative. Number 2 method is the cylindrical method, or the shell method. So this is the method we use when the axis of rotation is parallel to the integration variable. It usually revolves around the y-axis with integration with respect to the x. So kind of think about it as like a perpendicular instead of like a parallel versus like a parallel versus, like a parallel versus a perpendicular. Or around the x-axis in respect to y. So the sum of, it's basically you're going to take like an infinite amount of thin cylindrical shells, right? And you're going to calculate their volume and then you're going to add them up. So we get this formula. Y-axis is going to be v is equal to a lower limit, b upper limit, 2 pi x, bracket f of x minus g of x, bracket dx. So I like using brackets because sometimes the parentheses get a little too much, and a bracket kind of helps us separate, where x is the radius of the shell and f of x minus g of x is the height. If you remember this correctly, this is going to be our inner function, right? And just to kind of reiterate, this is going to be our upper, our lower, and this is going to be the integrand. X-axis is basically the same thing. All you're going to be doing is changing the f of x to the f of y, and then the g of y, the g of x to the g of y, and then you're going to have a dy instead of a dx, where x is the radius of the shell and f of y minus g of y is the height. In electrical engineering, you're going to apply these to different things. So sometimes you're going to do like an antenna design for like a radio. So most of the radios are parabolic or horn antennas. So calculating their precise volume is crucial for resonant frequencies. If you've taken physics, it's basically the shape of the antenna, the size, the length, determine how far it can shoot its frequencies and what the pattern is. And the material also affects it as well. So the shape of a solid of revolution, it impacts radiation pattern and efficiency. And then there's also another thing in physics if you take, it's going to be basically your capacitors. You learn about them through electricity. Whenever you're doing component design in electrical engineering, the shape and the size of capacitors, inductors, resistors determine and estimate thermal analysis, basically how much heat is released. Often they are the solids of a revolution, right? So if you take a solid, you spin around, and that's what you get. So if you get a two-dimensional object, you spin it in a circle, you get a three-dimensional object. So the problem is that it gives us, we have to define R as a region bounded by the graph of the function. F of x is equal to the square root of x. And below the graph of the function is g of x is equal to 1 over x over the interval 1, 4. Find the volume of the solid of revolution as generated by revolving R around the y-axis. So basically, you have this pink thing right over there, right? It's this weird, like almost like a cone-like shape, and it's going to revolve around the y-axis. So it's going to go something like that. Okay, so it's going to go something like that, spin around. It's going to make a little bit of a washer kind of symbol. So if you take this object and you spin around, that's what you're going to get. And from there, what we can do is we can actually move on to step 1. So without further ado, let's jump right into the problem and let's see how we can do it. And for just clarity's sake, I might just do it in black. So step number 1, what we have to do is we have to choose the method. There's 3 different ones that I've shown you. What we're going to be doing is going to be the cylindrical method. Why? Because it shows the object on the x-axis, but it's going to revolve around the y-axis, right? So we're going to do the shell method. due to revolving around y-axis and defined by f of x and g of x. So basically f of x and g of x, they make this shape that's around the x-axis, but we're going to spin it around the y-axis. Next, what we have to do, identify our variables. So we know that this is a region, right? Region by R. So region R, what two variables do we have? We know that f of x is equal to the square root of x. We know that g of x is equal to 1 over x. So the f of x you shade above, you shade below for g of x. We know that the interval is between 1 and 4, and it's a bracket. Not a parentheses, a bracket. And the axis of revolution is around y-axis. So what formula do we use? We use this formula right here. V is equal to limit of a to the upper limit of b 2 pi x bracket the f of x minus g of x dx. So it's very, very simple. So from here, we identified the variables. What do we do now? So now we move on to evaluate the upper and lower limits. Over an interval. 1, 4. So at x equals 1, so basically what we're going to do is we're going to plug it into the two functions that we have. So f of 1, we're going to plug it into the square root of 1, because that's our function right there. It's going to just equal 1. And then if we do the same thing for g, so g of 1, if we plug it into the function, so 1 over 1 is going to equal just 1. And then at x is equal to 4, because 4 is our upper limit, it's going to be f of 4 square root of 4, it's going to equal 2. And g of 4 equals 1/4. And then we can also do one more. At x is equal to 2, and if we plug this into the f of 2, square root of 2, which is going to be roughly about 1.414. So for any region let's put for any x between 1 and 4, the f of x is equal to square root of x is greater than g of x, 1 over x. So basically the upper is f of x and lower is going to be the g of x. This is important because after this we have to set up the integrand. So v is equal to, we have the symbol, the integral symbol, 4, 1, and then 2 pi r. And if you remember correctly, well, what was our thing? It was the f of x, which is the square root of x minus 1 over x bracket dx. So if we simplify and rearrange this, what I like to do is I like to take the square root out because sometimes it's just weird. Okay, so we're going to take it out of the integral symbol because sometimes it kind of confuses me, and I think Professor Bell and Professor Dave even does this too. It just kind of confuses the entire thing. You can't leave it in there, but to me it just confuses everything. So we're going to rearrange everything. And rearrange. V is equal to 2 pi integral symbol, so we're going to keep everything the same. So there is actually an x right over here, if you remember correctly. What we're going to do is we're going to distribute the x too. So it's going to be x times the square root of x minus x times 1 over x. So what we can do from here is we can actually rewrite this in a different way. If you remember correctly, the square root of any number is the 1/2, right? To the raised to the 1/2. So it's x times x to the 1/2 minus, and then if you have any division, it's usually to the negative root, right? So x times x minus 1 dx. So in calculus, we have to start getting really used to like rearranging the numbers and just seeing them in a different way. So if you combine this, we can kind of pretend like x times x, right? So this is to the x to the power of 1. So if we write it like this, it makes it easier, right? So if you add this together, if you remember the sum rule, right? Whenever you have exponents and you multiply, x squared times x squared, what do you get? X to the 4th, right? So what happens here is you have the same denominator. We can write 2 over 2 is just 1, right? So we can write it as that. So what happens is x becomes 3 or 2 minus, and if you remember correctly, x, this is just like a 1, right? If it doesn't have anything, it's just a 1 minus x. So what happens if you do x to the 0 power? It just equals 1. So what this ends up becoming is x to the 0, or roughly about x to the 1. So I'm going to rewrite this to kind of make it a little bit easier. X is 0. Because 1 minus negative 1, sorry, 1 minus 1 is just 0. And 2 pi stays right there. Okay. For now, we're going to kind of ignore the rest, but what this ends up becoming is just 1. Don't forget to carry all your variables down. Sometimes it will mess you up. So from here, we move on to step 4. Don't worry, we are almost there. Step 4. We have to find the antiderivative. And then integrate in respect to x. So what we're going to be doing is we're going to be basically taking this integrand, right? So we're going to take this and we're going to throw it into the antiderivative formula. So if you remember correctly, it's going to look something like this. X3 over 2 minus 1 parentheses dx. For now, this does not matter. Okay, so once we do it to the antiderivative formula, what happens is the variable, right? So it's going to become like x3 over 2 plus 1 on top, and then 3 over 2 plus 1 in the bottom, minus x plus c. So how did I derive this, right? We have to use that same formula that we used in the beginning. So the antiderivative formula. Where did I write it? Let's copy this. Xn plus 1. Okay? So that is basically what we're doing. The constant stays the same, but we have to add a plus c to it. So the bottom becomes the exponent, which is just 3 over 2 plus 1. And on the top, we get an x over 3 over 2 plus 1. And if we simplify this a little bit further, what we end up getting once we get rid of the denominator is x over 5 over 2 minus x plus c, and which we can simplify even further to 2 over 5 times x to the 5 over 2 minus x plus c. Apologies. Let me actually recalculate this. So it's going to look something like, before we get to this step, it's going to look something like, so it's actually, yeah, there we go. Everything is good. It's going to look something like x to the 5 over 2 power minus over 5 over 2 5 over 2 minus x plus c. Once we get over here, then we can actually eliminate this. This needs to be moved over. There we go. That's a little bit better. And make sure you write things down correctly. Otherwise, it gets very, very complicated. Okay, from here, what we have to do is basically step 5. Evaluate the integral. Basically solve for x. So we plug this back into our equation, right? So we're going to get 2 pi. We're going to move 2 pi back because we are done integrating. 2 fifth x times 5, it's raised to the 5 over 2 minus x bracket. The upper limit's going to be 4, lower limit's going to be 1. So if we evaluate at the upper limit, so whenever you see evaluate, it just means solve for x. We're just going to plug it for an x. At x equals 4. And what we get is v is equal to 2 pi bracket 2 over 5 times 4 over 5 over 2 minus 4. So if we rewrite this, that's like basically like the square root of 4 raised to the 5th power times 2 to the 5th minus 4. And what this ends up becoming is just 2 raised to the 5th power, which 2 times 2 times 2 times 2 times 2 is going to give us 32. 32 minus 4 times 2 to the 5th. I have to write the v down. I just got tired of writing. So we get what we have to do from here is we can actually multiply this directly, but we have to convert the 4 into 20 over 5. The reason why is because when we multiply this, it's going to become 64 over 5 to get the common denominator. And then we end up with 44 over 5. That's our evaluate at x is equal to 4. And then we have to evaluate at x is equal to 1. So the same thing, but it becomes so much easier. Sorry, my allergies are acting up. 1 raised to the 5 over 2. I'll give you a hint. It's going to be even simple. It's not as easy as 0, but if you raise anything and the square root of 1 is always 1, right? So the square root of 1 is equal to just 1. And then if you raise 1 to the 5th power, it just becomes 1. So what this ends up becoming is just 2 over 5 minus 1. You can always do like times 1, but it becomes 2 over 5 minus 1. And if we convert this to a fraction form, so multiply this times 5 over 5, to 5th minus 5 over 5, what we get is negative 3 over 5. So okay. Step 6, we plug in our answers and subtract. So basically, if you remember from our big giant formula, we're going to get 2 pi, it's going to be 44 5 bracket 2 pi minus 3 over 5. We know that minus is going to make a positive, right? So it's going to become 47 over 5 times 2 pi. So if we distribute this, it's going to become 94 pi over 5. And that is our answer. Thank you so much for tuning in. I will see you guys next time. Thank you so much, Professor Bao. I want to list out my sources. So I used Professor Dave and his video. Of course, I used Professor Bao. I used her 6.1 and 6.2. And then I used Professor Dave in, there was a video he had of like calculating the volume using calculus. And then I also used my organic chemistry tutor and the disk method and the washer method, and then also the shell method. Thank you so much. Take care.